so it's been a long time. But let's rewind. Sorry, it's going to be bad. There's nothing I can do about it. Okay, so first of all, we had a long time ago, in 1800s, we had John Dalton. He said atoms were a solid sphere. He had the modern atomic theory. This was John Dalton. Okay, he was that crass guy. He had the first modern atomic theory. It's still true today. There are some adjustments. And then, of course, over time, we had J.J. Thomson, okay, who said that atom is a plum pudding model. He discovered the corpuscle, damn it, or the electrons. Okay, and then, of course, he went to Ernest Rutherford, who said, hey, the positives are in a small part of the overall size of the nucleus, or the particle was deflected by a high positive charge in a very small volume, the atomic nucleus. Okay, so we had that positive nucleus. On the outside, there were the empty space where electrons existed. And then I know this is what I've been boring you most with. Niels Bohr, okay, had where the positives were. And of course, the electrons weren't arranged haphazardly as J.J. Thomson or Ernest Rutherford. These guys were in distinct energy orbits that had specific energy levels, okay? Now, Bohr was the first to quantize the atom, meaning that the electron arrangement in the atom is where the atom has specific energy levels to either absorb or emit, okay? And that atoms do not accept any amount of energy, only specific amounts. Hey, going back in time where we had the ultraviolet catastrophe, okay, it was Max Planck who said that there was these oscillators in these black body radiators, or these things that glow when you heat them. Okay, well, it's the electrons that jump away or back toward the nucleus. That's these oscillators. Okay, now his atom was doomed. It wasn't perfect. He was only able to explain these electron jumps in hydrogen only. And the reason why he can only explain is that there is more to the story that he could not explain. Besides, he was using classical physical model and trying to give it some new quantum mechanical model, try to bring them together, and it didn't match. We found that the atom is not classical, it's more of a quantum mechanical model. So, but he was on the right path, okay? So this is monumentous. Now, from Bohr, led us to the current model. The current model of the atom, which we still held today. And sometimes we call it the wave mechanical model. Okay. Model. All right. And then we have the wave mechanical model. Sometimes they call it the electron dot model. Okay, now what's different about this model? Very important. Electrons don't exist in specific orbits. They exist in specific orbitals. So orbitals is a word, it sounds like orbit, to give Bohr a lot of credit, because he was right. It was the electrons that had specific energies, but they weren't in circular orbits, okay? 2, we can never look at a single atom and do any of this type of mechanics. Mechanical means mathematical model, okay? Wave mechanical means we're treating the electron as waves, not particle. So we're talking about waves for electrons. Electrons are existing as waves from de Broglie's formula. And 3, this model of electrons with specific energies is based upon probabilities, okay? Very important. So in the current wave mechanical model, okay, electrons are not in circular orbits, they're in distinct energy places. But they exist as standing waves of probability of where they're at, okay? And there's still something to be said about their distance, okay? We talked about proximity, okay? So when I draw for you the current wave mechanical model, okay, here's what it looks like. Okay, if I'm going to draw helium, okay, I may have a nucleus here, and sometimes they'll draw this set of axes to show the nucleus is right there. But bottom line is, you would get something like this. And if I keep going, meaning there's a wave of probability of helium in that position. Is the electron a dot? No, it's a wave. So electron dots are kind of weird, but the idea is that there is a standing wave of electrons that exist in this spherical area. Where exactly is it? Don't know. It's a wave of probabilities. You could say with high probability electrons in anywhere in this area. And of course I just drew for you a what? A spherical orbital for helium. Helium, okay, if you look at helium, it has 2 protons, it has 2 electrons. I say atom, you say what? Therefore, +2 in the nucleus, called a nuclear charge, you must have 2 electrons to balance that off to make it. So the configuration would be 1s2, as we did last week. So I didn't draw 2 electrons, that's just a wave of probability where electrons exist. If electrons exist in a p orbital, what's that look like? And again, it's just a wave of probability. Okay, so that's the current model. And interesting enough, there's an equation that we use, okay, and there are many equations that people use for different reasons to explain the behavior of atoms, but we all use them in terms of waves and probability. But it was Erwin Schrödinger's equation that helped us understand these energy levels that exist in these 3-dimensional areas called wave functions, okay, that are based on discrete energy levels, like Bohr said, but not circular orbits, okay? Any case, from that Schrödinger equation, which is one interpretation, and there's many that work very nicely, we have a way of putting electrons, arranging them in terms of their energy to show where they exist and to start thinking about their properties because of that arrangement. And that's what electron configurations are. We did that Friday, and we're going to a couple Fridays ago. Before we do so, I want to quickly remind you that from the Schrödinger equation, which is an interpretation of this model, or an application of this model, we get 3 quantum numbers. We're going to add the spin in later. That came from the other side, but combined, we have 4 quantum numbers. And the quantum numbers are solutions to Erwin Schrödinger's equation that helps us visualize where electrons are. The other interpretations of quantum mechanics aren't as nice in visualizing and having a place to put electrons. They're just pure equations. So the quantum number form you had last Thursday, it's been a while ago, but I want to go over it quickly. Okay, quantum number index is the size. Okay, a 2s, a 3s, and a 4s are becoming 3 spherical areas of probability where electrons can exist as a wave. And as you go from 1s to 2s to 3s to 4s, hey, these guys get less stable. They're physically farther apart. The n number always indexes how coulomically these electrons attract the nucleus by distance alone. One of the factors of how well an electron can exist or be stable. These are words you have to get down. Being stable means that you have low energy and the nucleus attracts you strongly. So as we go from a 1s to a 4s, the stability of the electron decreases because coulomically the distance is far apart. Remember, I did the light. It's an inverse square law, Coulomb's law. Remember this demonstration? The farther I get away, okay, it's the inverse square of the strength of attraction. So as I go from a 1s to 2s, this electron feels the nucleus 1/4 of that original 1s. This is what? 1/9, as you can see. That's how it works. So if the electron feels the nucleus less, we would say that it is loosely bound. It is less stable. Electrons, okay, are not tightly bound. It's important to get that as we go through this. But the n index is size and distance. Now, quantum number n can be any positive number? No, it should read any positive integer. It can't be 1.5. It's 1, 2, 3, 4. It can go to infinity. Okay, obviously it does not. What does the L index? Hey, that index is the preferred axes, okay? And of course it tells you the shape. When L is 0, there's no preferred. Okay, there's one preferred, D has 2. So this gives you the fine tuning of the energy level, okay? 1s orbital has the following quantum numbers. Okay, absolutely, for reasons we should know from the rules. Okay, 1 is n equals 1, s is 0, and you only can have an s, okay, when n equals 1 for reasons we should already know. Okay, how many preferred axes does s orbital have? 0. There's no preferred, that's why it's a sphere, okay? And that's why of all of the different shapes we have, S, P, D, F, G, okay, this is the lowest energy, okay? What is the quantum number ML index? Okay, well this index is how many of one particular sublevel. If you've got an S, there's only one type, okay? And so therefore, it tells you, now it definitely tells you the orientations. Hey, a p orbital can be coming right at you. This would be the what? The p orbital, we can call it p y. There could be p x if it went out this way, and there's pz coming at you and going into the board. So these would be 3 different p orbitals when L equals 1, okay? There's 5 different versions. So this tells you all of them. And what we're going to learn tonight, these are all the same energy level. They're degenerate because having a different orientation, okay, think about this p orbital and this p orbital. I'll just do 2 because it's easy to do this. This is py and pz. Because they are perpendicular to each other, they don't get in each other's way. So therefore, they feel the nucleus the same amount because they are in a different, orientation of space. So they're not getting in between each other. So that's why they should be degenerate. Okay? Words that we're trying to pick up here. All right? Number 7. How many orientations does a P have? 3. And to figure out, you do your, if your L equals 1, you do -1 through +1, and you get 3 different numbers. We've been through that, okay? S only has 1 version, okay? And we've been through this. Pick the choice that represents one choice that's not possible, quantum number of 2p. If it's 2p, that means we're in the second principal shell or energy level. L has to equals 1 because, remember, L is 0 to n minus 1, okay? And therefore, m sub L can only have these 3 numbers because it's -L through 0 to +L to tell you how many orientations. Guys, these rules or these solutions to the Schrodinger equation are quantized. You can't have anything you want. One rule restricts the other. This rule restricts the other. Okay? So that's why we have a fixed set of how many electrons can exist in how many sublevels. These rules are linked to each other, and they fix the other rule in front of them. All right? What are the possible values of m sub L of a 3D electron? Well, if n equals 3, okay, L can be 0, 1, and 2. 0 is S, 1 is P, and 2 is D. 2 orientations in space. Hey, if this is a P, a D here's an example of a D. 2 orientations in space. Okay, and there's 5 of them. How do I know? Well, if L equals 2, -2 to +2, I get 5 different numbers, 5 different solutions of the same energy level orientated differently in the space. 10, at some point in the video I show you g orbitals. Where do they occur? Well, if you look carefully, look at this nice quantum rule. When n equals 1, you only have S. S and P, n equals 3. So the number of different types of shapes or sublevels always equals that. So the G does exist, but exists in n equals 5. Maybe we'll see today why that doesn't appear naturally. Maybe not. Okay. And then, of course, how many different type of orbitals in the 3D? We've done this. Third principal angel have 3. We just did this. What is the quantum number of electrons that the third principal angel can have? So what's the max number of electrons? Well, if n equals 3, here are the 3 possible sublevels. We know the S holds 2, P holds 6, D holds 10. You say, well, how do I know that? There's only one orbital for S, that's 2. There's 3 different orbitals. Each orbital holds a pair. Okay, so 2, 4, 6, 8, and of course 10, 12, 14, 16, 18. 18 electrons exist in the third energy level. Okay?
What's the -1, 0, 1?
That is telling, that's the M-Savell rule. That's telling you how many different, okay, orientations in space of the same sublevel. Like, for instance, P has 3. P has 1 that goes here. P has 1 that goes here. P has 1, it's hard to draw this one, going out to you and into the board. That's the Z. So this would be the -1, 0, and +1. If L equals 1. M-Savell is always these rules. Okay? So it's telling you, if you count how many of them, that tells you how many individual orbitals. And there's shapes attached to these, okay? We tend to make it simplified and use the boxes. Okay, enough said. Okay, so let's get back on our horse here, all right, and do some more of this. Okay, I have enough open already. Okay, so what I want to do is pull up the Christmas in July. I thought I had it open. Well, let's see what happens. There we go. There we go. Let's put up the reference table, and then we're gonna do some more of this together. Maybe if I can just stop. Oh, I'll leave that up. Okay, and let's start with sodium. So we're using this worksheet that I just gave you. If you're at home, you should have printed. If not, okay, bad students. Okay. So again, the purpose of what we're doing, now, this is absolutely must skills. There's a lot of things I taught you that I'm never going to see on an AP, okay? But I really believe it's important to connect the dots to see how I got from here to here. A lot of chemistry teachers will just teach you, okay, 1s2, 2s2, just learn it. Okay, but this is essential. This skill right here you must have and down cold. Okay, so I've got sodium. Okay, now sodium, atomic number 11. Okay, that's what we care about, which means 11 electrons. Now, interesting enough, in the worksheet that I gave you, the regions gives you a type of electron configuration. 2-8-1, we'll talk about that in a second. But let's go over the quantum numbers, okay? I want this quantum number. In fact, before we get to that quantum number, let's do the orbital notation, okay? My boxes aren't too bad today, if I say so myself. Okay, so there's something called the Aufbau principle. Electrons go from lower energy orbitals first. Well, electrons with the lowest energies are the ones closest to the nucleus. The ones closest to the nucleus are the ones with the lower n number, okay? So we should know that this is the 1s orbital. This is the 2s orbital. We should know that there's 3 p's. And this is the 3s. Now, in truth, they're not boxes. They actually are 3-dimensional shapes, but they draw the boxes to make it easier to understand. Okay, so what's my configuration? Well, the bottom line is I've got 11 electrons. So they're going to fill the lowest energy level first. So we draw opposite arrows right there. That means our configuration is 1s2. And from last Friday, the first 2 electrons fill the lowest energy level. Okay? That means we've just filled the first principal energy level. When n equals 1 from a quantum number, L can only be 0. L is an S. M-Savell is 0. Only one type, one box, one pair. Okay.
Wait, so what's the 2 from?
What's that?
What's the 2 from?
This 2? is how many electrons are in the s. The exponent is the electrons in that actual s orbital. Okay? Now we go to 2s. Well, 2s2. Okay? And if you notice, there's 8 electrons in the second energy level. There's 2 in the s, and there's 6 more. And we always draw filled orbitals with opposite spinned electrons because every orbital or every electron must have 4 different quantum numbers. So the spins have to be this. This is 2p6. And then now we're 3s1. Now, how do I do that? And how did I get there? Okay? We tend to call this the S block. Notice there's only 2 columns. There's only 2 electrons that exist in one orbital. We tend to call this the P block. Notice there's 6 columns for a total of 6 electrons for 3 orbitals. Don't forget, I'm drawing boxes, but these things are really what? 3-dimensional shapes. Okay, it's just easier, okay? So let's start with that. So I want to stop at sodium. 1s2 filled my energy level. 2s2, 2p6, 3s1. The periodic table was not built for the electron configuration. The periodic table was built upon repeating. That's why they call periodic properties. It's amazing that when we figured this out, it matched something that was built independently, looking at it from a totally different way. That's what's amazing about this. Okay? These guys are in columns because they have the same what? Chemical properties. They were put in order of their atomic mass originally before they understood atomic number from H. Moseley. He adjusted this a little bit. But we said, hey, this is getting heavier and heavier and heavier. I got a new atom that's heavier than neon, lighter than beryllium, but it's, I'm sorry. So we put sodium under lithium because it has the same properties. What's repeating is something we'll talk about at some point, but there is 3s1. Okay, let's do the quantum numbers. Now I'm going to do the quantum number for this electron. Understand that every one of these could have a quantum number that I could ask for. So, in the 3s1 electron, what's that look like? Well, n equals what? 3. Okay, I'm talking now. Now, when n equals 3, what can L be? The rule for L is what? 0 to n minus 1. So if n equals 3, I've got 0, 1, and 2. What does this tell me? There are three different orbitals. There is the S, the P, and now a D. But we're starting always in order. S is lower energy. So we're going to go, the azimuthal number is 0. Okay, M sub L. Well, the rule for M sub L, if you remember, is negative L through 0 to positive L. If it's 0, you only have one number, 0. And because you only have one value of M sub L, there's only one orbital for an S always. But there's 2 electrons per orbital. And the spin, the M of S, is going to be positive 1/2. We don't know who goes first or second, but we always go by convention, positive 1/2. Okay?
Can you say how to get there?
How'd I get where?
Oh, 1/2.
Okay, that's just what we found to be spin. This was found outside of Schrodinger's equation. This was found by Pauli exclusion principle. He found that every electron in an orbital by mathematics have to have a different spin. We don't know quite what spin is other than electrons moving in a different pattern, okay?
How do you get it?
Yeah, well, if one is up, the one up is positive 1/2, okay? The one going down would be negative 1/2. It's always one or the other. If you're in an orbital, in an individual orbital, the first one be positive 1/2, the second one has to be opposite spin, okay? All right, so what's next? Magnesium. Well, my gosh, people, Very simple. I'm adding one more electron. So if this becomes magnesium, notice 12. Notice under magnesium, what do you have? 2-8-2. We're changing the outermost electron. That's called valence electrons. And those are the most unstable. Now, before I get to magnesium, this is really, really important. And I forgot to do this, so I want to do this now. Notice in the upper right-hand corner of sodium, Na. Sodium's called Na because they use the Egyptian word natrium. Okay, but in any case, what's that charge? It tells you that sodium atom loves to become +1. Now, why? Yeah. Has it become +1? Well, it's going to lose its most unstable, least bound electron. So if I was to ask you to write the electron configuration, so underneath it, write this, Na+. Write this, Na. So this is the electron configuration of the ground state. Ground state means filling from lower energy to higher energy. Okay, write Na+ right next to it, underneath it. What would be the configuration of Na+1? Well, it's going to lose an electron from its least bonded electron. Which electron is the farthest away? Right. So it's going to lose electrons. So here's a configuration of Na+1. 1s2, 2s2, 2p6, done. It lost an electron. Why is it +1? Well, sodium has 11 plus in the nucleus, called a nuclear charge, 11 protons. And count, 6 plus 2 plus 2. It has 10 electrons. Do the math. There's one more proton than electron. Now, why does it lose? Because it's so gosh darn big and having a filled energy level is stable. So it has an ability to lose, and there's a thermodynamic pathway. Things in nature go from high energy to what? Low energy. Concentrated source of energy disperses. Sodium loves to lose, oxidize, because by losing that outermost, it becomes as stable as neon. Last week we did, well, I know it was a while ago, what was the configuration? 1s2, 2s2, 2p6. We fill everything, we're very stable. These guys don't react. So it's one away from losing, or it could gain 7 to be like argon. It can't gain 7, but it can lose because it's a big atom. We talked about this. This is one of the reasons why it oxidizes. Okay, let's continue on to magnesium. Okay, Mg. Now it's 2-8-2. By the way, this is the configuration you would write for the regions. This is what we do in real chemistry in the rest of the world. Okay, now, so we have one more electron. Because of the Aufbau principle, electrons must fill from lower energy orbitals to higher. We are forced to put electron and fill that S first before we go on. So we are going to put that electron here. Now notice something. This one has to go down. If electrons are in the same orbital, because of the Pauli exclusion principle, every electron must have this 4 different quantum numbers. The only thing that's going to change here is what? -1/2. Everything else is the same. Okay? So what's the configuration of the magnesium atom? 1s2, 2s2, 2p6, 3s2. Now, a couple of things you should know as we go through this. This is a filled principal energy level. Hello? This is a filled principal energy level. Hello? Okay? We have 2 electrons outside a filled principal energy level. Now we know filling stuff is stable. So this thing could gain 6, or it could do what? Much easier. Lose 2. what is the charge in the upper right-hand corner of your magnesium? What does it tell you? It tells you that magnesium loves to become what? +2. We now know why. It's not as big. Going across, it gets a little smaller, but it still is a metal. Metals hold on to electrons loosely, so it's easier for it to lose 2. So what would be the electron configuration of magnesium +2? Well, it'd be 1s2, 2s2, 2p6, and what would it lose? The 2 most loosely bound electrons, the most unstable. And that's it right there. The reason why magnesium becomes +2 is because it can easily lose those 2 outermost to become like a noble gas. They don't become a noble gas, they become like in terms of energy levels. The only time you become like the other element is the same proton number, but they become stable. Okay? So magnesium loves to oxidize and lose 2 electrons. Okay? All right, moving forward. And notice something. It has 2 filled completely energy levels. Perfect. All right, let's move on to the next one. What's the next one? Aluminium. If you're from England, we say aluminium. Okay, so aluminum. Can you guess what this looks like? Aluminum. Atomic number 13. Okay? Its electron configuration, written for you in the Regents reference table, is 2-8-O3. We're putting a 3rd electron in there. We can't put a 3rd electron in an orbital. Why? We're either plus or minus a half. There's no 3rd choice by the Pauli exclusion principle. So, what are our choices when n equals 3? We have the S, which we just filled. The second highest energy level now is when n equals 1. That's the P. Now, okay, hold on. So now we have L. Right now I'm doing, just talking about why we have to introduce P's. Now P, if L equals 1, if it's a P, by our rules, M sub L takes this thing and goes negative that through 0 to plus that value. And you can see how many different solutions do I have? 3, which tells me there are 3 types of the same P sublevel. What differs is their orientation in space. So guess what? I've got to add 3 boxes. This would be my 3p, but I need 3 boxes. Each box represents an orbital. So, back to reality. So aluminium, here we go. We're stopping here. Watch, up here, watch. 1s2 filled, 2s2, 2p6 stable, 3s1. Ooh, we are starting on the P block. 3p1. 3p2, 3p3, cp3p, sorry. So this is 3p1. So we go 1s2, 2s2, 2p6, 3s2, 3p1. So 1s2, 2s2, 2p6, 3s2, 3p1. Quantum numbers. Well, if I'm going to do a quantum number for this box, this is going to be a 1 for the P. M sub L has 3 things. It's what? -1 through 0 to +1. We'll start with -1 there. And because we're dealing with the first electron, we always start with the spin going up +1/2.
Wait, why is L1?
+1/2. That's the spin going up. All right? Now, what is the charge of aluminum? What does it like to become? +3. Can you guess? Think of it with me. Watch. This is the first principal energy level filled. This is the second principal energy level filled. This is not filled. So, party people, this represents core electrons. These core electrons are in smaller n numbers. They are what? Closer to the nucleus by proximity. They are tightly bound. They are stable. These electrons here are called valence. Valence electrons. These are unstable. How do you know your valence electrons? These are the electrons that are not in a filled energy level. They are outside these core. These are what get passed around in bonding. Aluminum, as we saw in our redox, loved to react. It loved to give off electrons. It's a very reactive metal. Its oxidation potential was very positive. It loved to oxidize. And it was giving off these two electrons. Why? Because when it gave off these outermost electrons that are farther away, feel the nucleus less, we are left with these core that are stable. It got stable. Why can it do so? It's a big atom. It has the ability to do so. But the why is because by losing 3, it achieves stability of a noble gas, which don't react. Okay? All right. So, how does it become aluminum plus 3? So this is aluminum. And of course, the configuration of aluminum plus 3 is the same thing except the outermost 3. 1s2, 2s2, 2p6. If you notice in the last 3 that we did, they all have this, the neon's electron configuration. All right? Moving on. A little farther. We'll take a little break. Okay, let's do phosphorus. Hey, P. Atomic number 15. If you look at its electrons, 2-8-5. Maybe they give you this. It's crazy. They don't give you that on the AP, but okay. All right. So, anyone figure out how many valence electrons phosphorus has? What are the outermost electrons, not any filled energy level? 5. Okay. Okay. Now, let's do P in the periodic table. 1s2, 2s2, 2p6, 3s2, 3p3, 3p3. 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, right? 3p3. Yep. Now, mistake people make, they do this. Oh, there's 3 electrons in the p. Mistake, I'll do this. And that's incorrect. That's an incorrect way to add 2 electrons because of Hudd's rule. Hudd's rule, and you're going to go over this tonight with your homework. Hudd's rule states that if you're in the same degenerate orbital, multiple orbitals from the same sublevel have the same energy. So why would an electron pair itself up with another negative? Won't they repel themselves a little bit? Why would they pair up if there's another place they can go? And we always put them with the same spin because experimentally we have seen that. Okay? So that's 2p3. If you didn't see that with the s because there's only one orbital. Okay, so that's 3p. So this is 1s2, 2s2, 2p6, 3s2, 3p3. There's your filled first principal energy level. Here's your filled second. And we haven't quite filled the third yet. How many electrons exist outside a filled principal energy level? 3 plus 2 is 5. There are 5 valence electrons. Can you guess how many valence electrons does nitrogen have? 5. How about arsenic? 5. How about antimony? 5. They didn't know about electrons. They didn't know about quantum mechanics. They built this in 1860. What they recognized is that nitrogen, phosphorus, arsenic behaved chemically the same, similar. They didn't know why. They just put them under. Hey, this is heavier than this, but they put it under each other. We now know why. Having the same number of valence electrons makes them react very similarly. Okay? That's what opened the eyes of this. Okay. What is phosphorus charges? Okay? Now, if you notice something, you'll see -3, +3, and +5. Take the top charge, -3. That's the one that happens most. What? Well, phosphorus is a smaller atom. Its ability to lose electrons isn't very good. So it likes to gain electrons, likes to reduce. Well, how many is it going to need in order to get filled? 3. The reason it likes to become -3 is because it gains. Hey, these guys over here, being big atoms, have a thermodynamic pathway to lose to get stable. These guys have a thermodynamic way to gain. These guys are close, and they have an ability to attract electrons. So phosphorus, check out nitrogen, check out arsenic, check out antimony. They all like to become -3 for the same reasoning. So these are going to gain 3. So what would this look like? This is phosphorus as an atom, and this is phosphorus -3. Okay, well, it'll be 1s2, 2s2, 2p6, 3s2, 3p6, which has the same configuration, okay, as argon. Okay, can you guess what charge sulfur likes to become? -2. What about chlorine? What about fluorine? You can see why they're in the same group. Who is the most reactive elements over here, you think? Who is so close to becoming a noble gas? These are the most reactive nonmetals. Who do you think are the most reactive metals that explode in water? They're so close just by losing one. Explains a lot. Who are the most unreactive elements? Anyone ever hear of gold? Anybody platinum? We made electrolysis electrodes of platinum because it doesn't react. There's a reason. They can't what? Lose enough or gain enough to get us stable. Okay? Take a break. Every bit of what I taught you here today, I want to keep teaching you, is you need to have those things down. We're going to work on that. Okay? If you're uncomfortable with quantum mechanics and don't understand the Schrodinger, I don't care. But it gets us to this position. There's no way I'm going to teach you 2s and 1s without reasoning why. They took quantum numbers out of the AP. But I can't teach electron configurations without them. And if people do, to me it's heresy.
I don't get how you know if L is like.
Oh, I didn't do the quantum numbers for phosphorus, sorry.
How you know if L is 0, 1, or 2?
Okay, everything's defined by the what? The rule above. So if L equals 1, then M sub L has a rule of -L through 0 to positive L. Well, that's 1, that's -1, 0, +1. There are 3 solutions, which means there's 3 sublevels. Okay? So if I do this number here, so the quantum number, if I ever ask for a test, and I will, give me the quantum number for that. Okay? That's n equals 3. Hey, that's a p. That's going to be +1. Hey, it's pointing up because in empty orbitals, they always go the same way, +1/2. Sorry, I believe understanding the quantum numbers helps you with the configuration. Whether you agree with me or not, I'm not budging. And when you see this in college, you're gonna people are gonna just like wilt, and you'll be like, I got this.
Okay, and then for like to find L, you do 0 to.
Yeah, to get L, it's 0 to n-1 rule.
Yeah.
So These are all what? Dependent upon the rule above. And there's what? Restrictions, because there's quantized values.
If it's like, then it would be like 0 through 2, like, or it would be
Yeah,
0.
so if when n equals 3, the L can be 0 too. The 0 is the S, we already filled that, so now we're on to the P, which is the 1. But when you have the 0, and you do this rule with 0, you're only going to have 0, which means you only have one solution, one orbital. That's why the S only has one orbital. But once you get to 1, you have 3. And then when you get to D, which we'll talk about tomorrow, D is what? I'm sorry, D is 3, is L equals 2.
Oh,
Okay, well, guess what you got here?
So 0 is like.
So it'd be -2, -1, 0, +1, +2, and you're going to have 5 solutions, or 5 different orbitals. Each holds what? 2, so a maximum of 10 electrons. This is the D block, right? 1, 2, you count 10. This is the P block, holds 6. S block holds 2.
So if it's like if L equals 1, then it's like S block, then it's.
L equals 0
Yeah,
is the S. L equals 1 is P. L equals 2 is the what? Is the P. Okay. Whew. All right. So we'll continue with that. And we'll pick up that tomorrow. All right. Did I do the absorption spectrum for you guys or no? Demo?
Yeah.
Okay. So I have one demo I want to do for you guys. Give me a second to set that up.
That's what I was thinking. If you go